lab carts start from rest, so their V0s equal 0. They're pushed along a level surface by a constant force. All right, so the force is constant, great, and that force over a period of time is going to provide an impulse, which will be a change in momentum, which is m delta v. So those are just the connections we're making at this point. Students measure the magnitude and duration of the force, which we see here. Oops. We see the magnitude of the force. We actually see the time it's exerted as well. And the data table is partially completed, and they calculate the final kinetic energy and the final momentum. Which cart has a greater kinetic energy at the end of the push? What we can see in this first case is that the F delta T is 10. That is equal to the change in momentum, and since the momentum was 0, the final momentum, the change in momentum is the final momentum. And so that 10 is mv, which is 1 times the velocity. So the velocity is 10. So if we calculate the kinetic energy there, we get 50. And we can actually work backward if we wanted. We could say the kinetic energy is 1/2 mv squared. The kinetic energy is given as 50, 1/2 of the 1, the v squared. What would that be? Well, 100 is v squared, and v is 10. So we could work forward or backward to find out that velocity is 10. Next, we must work forward. And so that 10, that same impulse, is mv, so that's 2 times v. And so we can see that the velocity is 5. Makes sense? Same impulse, twice as massive object would have half the speed. So now we calculate the kinetic energy over here, 1/2 mv squared. So 1/2 of 2, and the velocity is 5, so that's 25. So we get a kinetic energy of 25 joules. Which cart has a greater kinetic energy at the end of the push? Well, that's the 1 kilogram cart. Definitely not the 2 kilogram part. They don't have the same kinetic energy, and the relationship can be determined. We don't need the distance. All we need is the force and the time to get the impulse.